purpose of this video is to demonstrate the transport theorem. So what we want to find is the time derivative of an extensive property of a moving fluid. The time derivative is clearly done by taking a function at time t plus dt, removing the function at time t, and divided by delta t, where delta t tends to 0. An extensive property is a measurable physical quantity that depends on the amount of substance. For instance, if you have more substance, you have more mass, but the temperature stays the same. So the mass is an extensive property, but not a temperature. So the idea is that I have a function that depends on the volume, and I want to see how to take the total derivative of this function. I want to take the total derivative of an integral, where the integral is an integral of an extensive property of a moving fluid. So suppose that the black line of the black surface includes a volume of fluid. After time delta t, the fluid has moved a little bit, so now the new boundary of the volume is the red surface, which is a line in 2t, but you should consider it a surface in 3 dimensions. The function f that I wanted to take the derivative of is just the integral of something else. For instance, written as small f or rho multiplied by n. So f may be, for instance, the mass, which is the integral over the density of a volume of fluid. In this case, if f is the mass, then n is just equal to 1, and it's just the integral of density over the volume. So how do I take this integral? I have to evaluate the general integral over time t plus delta t in the volume that has shifted a little bit, remove the same integral evaluated at time t, and divide by delta t, where, of course, delta t goes to 0. To make this difference, I can notice that I can separate the 2 regions. One is the orange region, where it is the same volume that is considered. And then there is the green region, due to the fact that this volume, the volume within the black boundary, has moved a little bit. So the green volume is just a very small quantity if delta t tends to 0. And basically I have to add this part on the right and remove the rear part on the left. So this integral is the total derivative of the orange area, which is the orange volume, which is constant, and of the green volume. Actually, the green, I have to add the right part and remove the rear part. So for the orange derivative, there is not much, there are not problems. For the green part, I have to evaluate this small volume. So I have to make the integral of all the green volume, which is separated by different steps. Each part can be computed. The small delta V green can be computed as the surface, delta S, multiplied by this short distance. And the short distance, if the surface has moved with velocity u, then the distance is u multiplied by delta t. And the small volume, or small green volume, is just the integral of the surface multiplied by this distance, u delta t, and the 2 must be multiplied by accounting also for the different direction. If I really want the volume, I have to multiply one by the other, but also consider the cosine of the angle. And this comes naturally if I take the scalar product of the direction of the velocity u and the direction normal to the surface. And if I take the outward normal n, I also have the advantage that on the right part, the outward normal is has the same verse of u, so that this integral is positive. And in the rear part, in the left part that I had to subtract, the outward normal and u are different directions, so that the cosine is automatically negative. So basically the integral, which is this second part, the integral in the green area, is the integral over the surface of this delta S multiplied by the normal, outward normal, scalar product with u, and multiplied by delta t. And of course, I also have rho n of t. Note that delta t is cancelled by the, and so delta t goes out from this second part of the second term. What stays here is the integral of the orange part, the total of derivative in the orange part, and the green part becomes a surface integral of rho n u scalar product n over the surface. And notice that this will be positive in the right part and negative in the rear part. So basically, we have demonstrated the theorem. Just see that since the orange part is fixed, the derivative of the total derivative can come inside also the integral. So that we have demonstrated the Reynolds Transport Theorem. The total derivative of this integral is the derivative of the local part and plus the flux of f multiplied by the velocity and integrated over the area. What velocity? This is the velocity of the boundary. But if we consider a volume of fluid, then the boundary moves with the fluid, so that u, of the velocity of the boundary, is also the velocity of the fluid. So this is the general form. Last comment is that I can transform this surface integral into a volume integral using the Gauss theorem, and take everything under the volume integral, so that they have the first term, the local derivative of a function, which in our case is rho n, plus the divergence of the second part, rho n u. So we managed to find the total derivative of something like mass, if rho is, if f is just a rho, or momentum flux. Thank you.